Hello and welcome to the CS4 interview. Joining me this week is Daniel Polani from the University of Hertfordshire, who's going to be talking about the action-perception loop. Daniel, welcome.
I'm glad to be here. Thank you for inviting me.
Lovely to see you. Now, you are a reader in artificial life, which means that you are a senior researcher in a subject that probably most people have never heard of. Can you tell me what is artificial life and how did you end up making a career in it?
Artificial life is basically a term that Chris Langton introduced so aptly as studying forms of life as they could be. Mm-hmm. And what I really like about that is a mixture of things that are, of course, biology, but not the biology only as we find it. People ask about how could other forms of life look like. Of course, based on carbon-based life, perhaps silicon-based life, but actually the question goes far further beyond that. It goes beyond if you had a different type of physics, entirely different, different computer game, different simulation of the world, could we still get life? And what would be the conditions to get something that we could call life in some suitable sense analogous to our actual biological life?
Okay. So would it be right in saying there's maybe two components to artificial life? There's the stuff which maybe people have heard on the telly, which is like the synthesis of new kind of artificial bacteria or something, but then there's the more arguably theoretical, conceptual notions of, you know, what is life?
Yes, I would say I'm more strongly on the second side, because I'm interested in the question, what are the necessary ingredients for life to emerge? Necessary on the level, of course, of biological requirements, but ideally, big picture, perhaps even on the physical level. So what properties must physics have so that life can emerge?
Okay, and you just mentioned physics. So your background was it mathematics and then physics, or? Physics
and math, yes. And then I went into artificial intelligence and very quickly got interested in neural networks, genetic algorithms when they were at the heyday, essentially. And from there, my interest expanded into complex systems. Actually, I had an interest in complex systems since I was an undergrad. I basically encountered a book by Herman Haken on synergetics, and it was sold on a cheap book sale, and it hooked me. And I thought that may have influenced me. Retrospectively, I think it has influenced me. Okay,
okay. So how much of your work is what people would understand to be artificial life, and how much of it's sort of more, you know, complexity science? Is there a particular well-defined field that's called artificial life, or is it maybe a subset of complexity science or something else?
Very good question. I would say I would probably be more on the artificial life side on it, because I always have the cognitive or biological aspect in mind in my work. But the complexity science is a necessary ingredient for anything we're doing, because life is a complex system. It's a very particular type of complex system which has the ability to form new levels of organization. And so it is a particularly interesting complex system. So I would say it's not a clear barrier. Of course, complex systems are probably more general than that, but I think artificial life is a very good, sizable portion of that type of research.
Okay, okay. So you're talking about the perception-action loop today.
Yes.
What's that then?
Well, organisms, almost every organism basically observes the environment, takes decisions, and carries them out. This is the main distinction intuitively, of what organisms are, how organisms are different from physics. Physical object is just there and being pushed around, if you like. An organism doesn't let itself being pushed around. It has some kind of decisions that it takes. How that comes about is a very deep and interesting question, but essentially we are not today concerned with that. Today we will just study what are the conditions that an organism has to fulfill in order to make decisions. And it turns out, to make decisions you need information. Information in the hard sense, not just in some kind of wishy-washy fuzzy sense, very hard sense, information as reduction of entropy, if you like, and you can quantify that, and you can put limits on that. You can, like the energy conservation theorem in physics, there is also some kind of theorem of conservation of information in a way that you need a certain amount of information to carry out certain decisions. And from there you can start and develop all kinds of questions. what can you do with such a statement. Once you have a conservation theorem, you can do a lot of things with that. You can ask transformation. In physics, there's transformation of energy. In biology, you could say transformation of information. Information is more difficult a concept than energy because it's not additive. You can't add up information easily. So it becomes more complicated, and that perhaps is why cognition and biological life is more complicated than physics in some respect. That may be the reason, but this is pure speculation. I'm just speculating at this point.
Okay. And in your title, or at least in your abstract, you mention Ashby. Ashby, one of the founders of the British cybernetics movement. And you talk about, I think it was the law of requisite variety?
Yes.
Which is notoriously hard to pin down. We might talk about that in a bit. But cybernetics, I think some people feel, was a bit of a failed movement. It's had its day in the 50s or 60s or 70s maybe. But I guess you still feel it's relevant to current day research issues?
Well, I always find this argument about failed directions quite moot. And the reason for that is research is about exploring various places, and it turns out sometimes there are some directions which are easier explored. And when in the 40s people decided to look at artificial ways of cognition or thinking, there were two models. There were the von Neumann model, which turned out to be extremely successful, and there was a cybernetics model which was very ingenious, but at that time nobody knew how to actually push it further. You got to a certain point and then you got stuck. While the von Neumann model, people knew exactly how to push it further. And that is how it develops. But at some point, the von Neumann model, of course, it brought us the computer, the PC, and everything, all the contraptions we use today. But on the other hand, in terms of understanding intelligence, it has failed us. If you look at chess, we have chess computers that beat Kasparov, the best chess player in the world at that time. Still, we don't understand how humans play chess. We have not understood anything about the intelligent process that happens in the brain. It's clearly not that we are computing 1 million moves per second. Mm-hmm. So we haven't understood it. In other words, that line has not got further, so the question is, let's look at different lines. And then, of course, it's called cybernetics. We can rename it, redub it with a different name. Doesn't matter. But the cybernetic movement has discovered that embodiment is important, or that the role of the physics, involving the physics in your decisions, is important. And that is one thing that I'm a proponent of, that information processing is costly, and so you want to process as little as possible if you can do that. And being parsimonious on processing costs is something that Ashby essentially is implying in this law of requisite variety. He doesn't say that explicitly, but in fact it's already implied in that statement by saying, I need to make a decision, I need information to squeeze down my state space. Well, I have to take this information in, and if I do that, it means I have information as a resource. Once it's a resource, it's expensive. If it's expensive, I want to be parsimonious. When I want to be parsimonious, I get a minimality principle. Get a minimality principle, I can compute things. And suddenly everything comes from there. And you can do a lot of interesting predictions coming from this type of attitude. So cybernetics, in my opinion, was, in hindsight, in my opinion, on the right track. But, of course, cybernetics also at that time perhaps did not have all the tools we have today. Yeah. We are much further in tools, and of course when the tools come together suddenly, things that looked really impossible become positively easy.
Yeah.
That is one reason why I also argue always that in foundational research it's not a good idea to say, oh, it has to have this outcome or this specific use, because you never know. If you develop a tool, that tool may become relevant 50 years later. You never know that.
Yeah. So, I mean, in that respect, it was quite ironic, because what were thought to be the hard problems in good old-fashioned AI, like getting a computer to play chess well, actually proved to be the easy kind of questions. Yes. And the hard questions were, how would you get an agent to even interact and move the pieces? So it's interesting you discussed the fact that it's only now, perhaps, that we're having the kind of mathematical tools, or even the computational tools, that we can perhaps take the cybernetics ideas a little bit further. So I certainly think that in terms of the work we do here. So we've got large supercomputers, and we can do computationally expensive simulations that maybe just 5 years ago would not have been feasible. So I think there is certainly, I would agree that tools, techniques and computing powers coming up to speed to maybe help us take what Ashby and the other founders of cybernetics looked at 40, 50 years ago, see if it actually can make some useful applications. So you alluded again to requisite variety. So can you give me put you on the spot, a nice pithy definition of what Ashby's law of requisite variety is?
If you want to reduce entropy in your environment by a certain amount, say 1 bit, you need to have a sensor that takes in 1 bit from the environment.
Okay. So I kind of struggle with the ideas that the controlling system must have at least as much information as the kind of system it has to control. But the problems with my kind of formulations today are rather woolly, and they're often verbal, whereas the potentially exciting thing about your research is that you are trying to quantify it in terms of entropy, in terms of information.
Yes.
And then you argue you're going further. There's a notion of optimality.
Yes, I mean, there are two things. Touchette and Lloyd made this really important contribution where they had a version of what I understand to be Ashby's law in the reduction of information. What we would like to suggest that, of course, this information has to be processed in your brain. Not necessarily in your brain, it can be more complicated. In my talk I will talk about that. But when you process it, then of course you want to use as little of it as you possibly can. Now, that is not necessarily the case. You could be very wasteful. Why not? Why don't waste a huge brain on processing 1 bit? Well, the argument is evolutionary, because processing information is expensive. It's used up a lot of metabolism. There's lots of evidence for that. And we know that sensors, for example, many organisms have very sensitive sensors. We know that there are toads whose eyes can recognize individual photons. So it means that we are operating in the biological realm at the limits of informational capacities. That is an indicator that information is, one, very important. The metabolic cost of information processing, brains, is very high, 20% say for a fly's eye, it's estimated. There are different various numbers, the error bars are big, but it's definitely a lot. It's a lot of, imagine 20% tax, essentially, just for the eye. Or even 10%, it's a lot. And what we are saying here is that obviously the evolution is ready to pay that tax for that amount of information. So it's important. And of course, if you can process less, you will. Because you will have an advantage, you will need less food, you can propagate faster, and you have these various fitness advantages if you could do with less. So we argue that balanced systems, adapted systems, so systems that are not entirely in the flow, but basically where they are found their niche and adapted to it, will operate on a trade-off curve between fitness and the information processed. They will want to get the highest fitness for the given information processing cost, or the lowest information processing cost for a given fitness. Mm-hmm. That is a hypothesis that gives you a curve, basically a Pareto curve, if you like. And this Pareto curve, we believe, it can be computed in very simple models, gives you a predictive statement about where you expect biologically plausible cognitive solutions to be.
Okay, so just as we could imagine evolutionary arms races for bigger teeth and stronger limbs to run faster, there could be a strong sense of an evolutionary arms race for more efficient processing of information.
Exactly, and for more efficient sensors. And sensors, as I said, they're very expensive, but they're still cheaper than having a bigger body or faster body. And so if you have a good sensor that can detect a predator far away, and that saves you running away from this predator, it's a good investment. Mm-hmm. And we would argue that, in fact, that explains why there are so many different sensors in animal kingdom.
Okay.
Very, very qualitatively, of course. It's not a quantitative explanation, but would explain why that is really the case.
And these are the same kind of concerns that engineers have when they come to design, autonomous vehicles, or even the tiny little drones. how can you pack as much information processing and sensor information into those kind of systems? Is the work that you do, are there direct applications to engineering endeavours?
There are, but they're not as direct as it would be as indicated by you. And the reason for that is basically that we are exploring various routes. But of course, what you're saying is very interesting. One engineering application I could imagine would be one where you say, okay, I have this drone. It doesn't have to be very precise. It doesn't have to be very accurate. It has just to collect temperature data, say from a certain area. And then the question is, what is the smallest in terms of information processing, contraption of sensors, processing actuators that would be good enough? So it doesn't have to be perfect, not the highest quality, cheap. It's a simple, what's the cheapest solution you can find? And that's something where we can probably say something about, at least in principle. And this is the type of statement we are able to say. But also we can predict, or we believe we can predict, how, if that hypothesis is correct, of course, how organisms will behave under certain constraints. One can make certain predictions. We have, for example, one little prediction we made where we say, if you want to go to a goal, and you have to remember where you're going to, and that takes up your memory. But if your working memory that has to make the decision based on that goal is limited, then you cannot hold everything in full memory. You always have to shift in and out what you know about your current goal. So I want to go whatever into the city. First I have to go through this door. I don't care about the city, I just have to remember to go through the store. I cross the door, I can forget about the door and remember my next step. In fact, there's psychological evidence, it seems, that people do have a tendency to forget things when they cross doors. In other words, a very bottom-up model, a highly simplified model with simple arguments on bandwidth and processing power, may be giving you an idea of how, even on very high cognitive level, things are being processed. And if that is in any way indicatory, means that this theory may have some predictive power, or also some kind of power to model some aspects of the hierarchy of the cognitive processing. Certainly not everything. There are certainly things we haven't captured with that, but some of them may be feasible.
It's certainly a very exciting idea that you could have such what seem to be trivially simple processes that could help explain, us complex and fascinating organisms. I'm afraid that's all we've got time for now, so thank you again for coming along.
It's a pleasure.
I look forward to your talk later on. Thank you.
Thank you very much.